Before computers can think, they must decide. At the heart of every digital system lies a simple concept: binary logic. Everything is reduced to two states, 1 or 0, true or false. But how does a machine physically represent these states? The answer is the transistor. A transistor is a tiny electronic switch. It can either allow current to pass or block it. When current flows, it represents a 1. When it doesn't, it represents a 0. By combining millions, or even billions, of these switches, we can create circuits that perform logical decisions. These decisions are built using logic gates. A logic gate is a fundamental building block that takes one or more binary inputs and produces a single output based on a rule. From this simple idea, all digital electronics are born. The simplest logic gates form the foundation of all digital systems. First, the AND gate. An AND gate only outputs a 1 when all its inputs are 1. If even one input is 0, the output becomes 0. This gate represents strict conditions: everything must be true. Next, the OR gate. An OR gate outputs 1 if at least one input is 1. It is more flexible, only one condition needs to be true. Then comes the NOT gate, also known as the inverter. It has only one input. If the input is 1, the output becomes 0. If the input is 0, the output becomes 1. It simply reverses the signal. These gates are built using transistors arranged in specific configurations. By controlling how current flows through them, each logical rule is physically implemented. From these three simple gates, complexity begins to grow. As digital systems evolved, more powerful gates were developed. The NAND gate combines an AND NOT. It outputs 0 only when all inputs are 1. Otherwise, it outputs 1. Interestingly, NAND gates are universal. Any logic circuit can be built using only NAND gates. The NOR gate is the opposite of OR. It outputs 1 only when all inputs are 0. Like NAND, it is also universal. Then comes the XOR gate, exclusive OR. It outputs 1 only when the inputs are different. If both inputs are the same, the output is 0. This gate is essential in operations like addition and error detection. Finally, the XNOR gate, the inverse of XOR. It outputs 1 when inputs are the same, and 0 when they are different. Each of these gates is built by combining transistors in more complex arrangements, allowing more advanced decision-making at the hardware level. Individually, logic gates are simple. But when combined, they become powerful. Thousands of gates form circuits like adders, which perform arithmetic. Millions form processors, capable of executing programs. Billions create modern CPUs that power computers, smartphones, and artificial intelligence systems. Every operation, every calculation, every image, every sound is processed through layers of logic gates working together. At the lowest level, it is all just transistors switching on and off. But together, they create something extraordinary. They allow machines to compute, decide, and respond. From a simple switch to complex intelligence. Logic gates are the invisible language of digital electronics, the foundation upon which the modern world is built. And every time you use a device, billions of tiny decisions are happening in perfect harmony. And now, you've seen what happens behind the screen. From tiny transistors, to powerful logic gates, to intelligent systems shaping our world. This is just the beginning. Technology is evolving every day, and the more you understand it, the more powerful you become. If you enjoyed this journey into the world of digital electronics, take a moment to support the channel. Like this video, so more people can discover it. Subscribe to stay connected and explore even deeper topics in technology, science, and innovation. And don't forget to share this video with others, because knowledge grows when it is shared. Your support helps bring more ideas to life, more explanations, and more discoveries. The future is built by those who understand it. And this is your step forward. See you in the next video.